Okay, thank you. Thanks for the invitation to speak here. Let me get this out here right away. Everything I say today is really a joint work from a few years ago with Jason Bell, Mattias, Jonsson, and Holly Krieger. So what I want to talk about, let me get the theorems up on the board right away, and then I will deal with them. So the theorem advertised is in every dimension bigger than or equal to 3, there exists a birational map. From PD to itself, such that, or with transcendental first dynamical degree. Okay, which I'll denote by lambda of f. And since it's the only dynamical degree that will come up for most of this talk, I'll omit the first most of the time. I should say a few things. Well, actually, let me get there's a precursor to this theorem that I kind of want to talk about in parallel because it's a little simpler to expose. Bell, Jonsson, and me proved this theorem. There exists a rational map of two variables with the same conclusion. The first dynamical degree is transcendental, okay? And the two theorems, the path to the proof in the two theorems is similar, but the first one is substantially more complicated than the second one. So I will actually say things about both of them here. I've also tacked up some notes for this, but I've been afraid to upload them so far. I promised I'll upload them this afternoon. The problem with tech is when I write things in tech, I feel like I'm promising there are no mistakes. That's very much not the case with what I'm going to upload this afternoon. It's, think of them as handwritten notes that just, I fed to ChatGPT to tech up or something. Okay? All right. What do I want to say first? I know you guys had a whole bunch of lectures. If you were here for the past couple of weeks, you had a whole bunch of lectures on dynamical degrees. Nevertheless, I'm going to give some definitions in history. So my plan is as follows. Start with a bit of history, which if I'm repeating things you know well, forgive me. And then I want to talk particularly about monomial maps and toric defolds, so toric blow-ups of projective space here. Then I want to introduce the map of interest, F, and give a power series formula. For its first dynamical degree. Okay, so this this is, I really hope to achieve all this today. All right, this is where all the geometry takes place. And then there's kind of an interlude where you reformulate the power series formula. turn it into something that looks fairly different than what you started with. And then once you're done with this, all the geometry goes away. And from this point forth, you can kind of forget where the formula comes from and just focus on the transcendence part. So then, next time, I don't know where this goes. Next time will be the number theory and conclusion. So the lectures will be, in some logical sense, pretty independent of each other here. Okay, so for my purposes, you can use a pretty elementary formula for a dynamical degree. So given a rational map, when I say the degree of f, I just mean the degree of f inverse of h, where h is some sort of general hyperplane. Okay, and it's so instead of thinking of inverse image, if you don't want to say general hyperplane, if you want to say any hyperplane, you can pull it back as a divisor and intersect it with some line. Or finally, what I'm going to do is map the whole thing forward and compute the degree this way in this talk. Okay, so when I compute degrees, I'm basically going to be doing this in this talk. All right, so remark, if f is a morphism, then iteration and degree cooperate very well. We have this condition that the degree of f to the n is just the nth power of the degree of f. Okay? Here we're getting into the history. The first place I ever saw this, at least, there's a paper, FS, Fornes, and Sibony observed that in general, this doesn't have to work. Okay? Sometimes you can have less. Okay, they just pointed this out. And Russakovsky and Schiffman, this is back in the 1990s. So Russakovsky and Schiffman pointed out then that even when you had less than here, these degrees have an exponential growth rate, okay? They observe that this limit exists. Okay? And this is my dynamical degree here. Okay, so that's the 1990s. So quick example. You just take this map where you swap the coordinates and square one of them, just affine coordinates. That's f. Then lambda of f is root 2. Okay? If f is holomorphic, you're going to get an integer. I should have said that first. Lambda of f in z if F is morphism, because it's just the degree of F. Okay, but the dynamical degree doesn't even have to be a rational number in general. You can easily cook up examples where the dynamical degree is like a square root of a number or something. What do I want to say here? This room it does not have a clock. Okay. One. All right. Right, and then there were some theorems that started to suggest that this is about as bad as it could get. Okay, it made us hope that this was about as bad as it could get. So at about the same time, a couple theorems showed up. So with Fav, we showed that if the dimension is 2 and the map is birational, then the first dynamical degree is an algebraic integer. Okay? And I'll point out that that's why there is no bi in that theorem right there. Okay? Couldn't happen in 2 variables. All right, another theorem, which is maybe even more suggestive, and it's due to Bonifant and Fornes. And there's an update of that theorem due to Urek from not that long ago, within the past 10 years. I forget, I'm not good with dates anymore. They all kind of run together. So the theorem says that there exist countably many possibilities for the sequence of degrees of F. Okay, so you take all possible rational maps in all possible dimensions, look at this sequence of degrees, and there's only countably many outputs here. And it's pretty easy to prove. So the idea is that rational maps are parameterized by their coefficients, and maps of the same degree, fixing the degree, picks out a subvariety in that variety. All right, so if you fix the degree, you get a subvariety. If you fix 2 of the degrees, you get a smaller subvariety, and you get this sort of, as you fix more and more degrees, you get a nested sequence of subvarieties, and this sequence stabilizes. You know, you have the Noetherian property that says eventually the variety drops to dimension 0 and no further. And from that, you just extract this fact here. So there's that. And I'll mention one more theorem that came a little bit later. It's due to Fav and Jonsson. And it says that if you have a polynomial map from of the affine plane, treated as a rational map of the projective plane, then the first dynamical degree is even more special. It's a quadratic integer. It's the root of a quadratic equation, monic quadratic equation with integer coefficients, all right? So, I mean, you start to see all these things and, you know, you believe maybe you have a guess at, you know, what could happen here with these dynamical degrees. I mean, I had hoped that, you know, maybe in general we could prove that these things are always algebraic. And the point of the theorems is, no, it doesn't really work, okay? Which is, to me, surprising, anyhow. Let me say something. I should say something about the proofs of the first and third theorem here, because it is sort of relevant for what comes later. So how to prove df and fj. So the idea is to show that in either case, the map you get on the projective plane is what I'll call stabilizable. All right? And what do I mean by that? i.e., there exists birational morphism it's a blow-up of P2 that lifts well, it'll lift F to some rational map on X, but the salient property here is that when you iterate pullback, it's the same as pulling back by the iterate here. Whoops, F, how about that? How about an N? Now it's a theorem. And what am I pulling back here? Well, divisors really, but I want a finite dimensional vector space, so I use numerical equivalence classes of divisors. Is that an acceptable notation for, what's that? One should be upstairs? Okay, thank you. Obviously, I was trained as a complex analyst, and it's going to show here. One way it's going to show, I should have said from the beginning, all of this stuff I'm talking about would make sense over pretty arbitrary fields. But for my comfort, not yours, the field is C, all right? Just let's get that out there. Okay, so you can lift F to a map that iterates well on divisors, but so what? Okay, so then, so how does this help? So now, what was my formula for the degree? The degree of F to the N is going to be, I'm going to pull back a hyperplane, and I'm going to intersect it with a line. And then what you check is that that is the same thing as I should put parentheses here, but I need no parentheses there. I can lift everything up into X and compute the degrees this way. All right? And up in X, this is, I'll emphasize, okay? Where everything here, the pairing, the divisor, the divisor and the curve here have numerical classes that are defined over integers, all right? So in some abstract sense, you have some pairing. Let's see, a to the n v u, where A is an integer matrix. U and V are integer vectors. And the pairing is integral. Okay, so you just end up with a nice linear algebra thing in the end. It's very concrete, defined over the integers. So this implies that the degree of F to the N, this sequence satisfies a linear recurrence. Relation, all right? This is just like the, maybe almost the definition of a linear recurrence relation here. And in particular, lambda of f is in q bar. So that's, in both of these theorems, this is what's proved. I should, full disclosure, you may have to go to f squared, I think, in the Jonsson theorem. You may have to take a power of f to get things to work here. Okay? So all well and good, and this is not the last time in this talk you're going to see expressions like this come up. Okay, so what I promised next. So that's, I think, all the history. Well, the next part is history too, but I want to put my own spin on this history. So now I want to talk about monomial maps. So definition. So given an integer square matrix A, I'm going to set HA of x1 dot 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 xd equals essentially x to the A, all right? But this is, so x1 to the A, 1, 1, and never can remember rows or columns, A, 1d dot 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 x1 to the A d1 dot 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 xd to the A dd. So I've got a linear map A, and I'm just kind of exponentiating it here, and that's my monomial map. Okay, so with this definition, observe that HA compose HB, if I've done this right, is HA times B, right? Works really well. And because of this fact, you get right away that the first dynamical degree of a monomial map is equal to the magnitude of the leading eigenvalue. Of A. Well, you have to think about it for a little bit. Okay, the sketch of the proof is this. If you stare at things, the degree of HA is about the same thing as the maximum of the absolute values of A. Not exactly equal to the maximum, but it is sort of comparable to that, okay? And so this maximum, as you take powers of A, this is going to grow like the magnitude of the leading eigenvalue, like the spectral radius of A. Okay, so it implies okay, if it's not clear by now, let me just say it. When I say proof, I don't mean proof, right? I'm saying sketch of a proof, idea of a proof. Yeah, that's, if I accidentally prove something completely, I wasn't intended. Okay. All right, but this, okay, so this implies something that looks like the previous theorem. So lambda of HA is, again, a quadratic integer. Okay, but that really hides some complexity, because if I just write down here, here's an A. What's that? Sorry. Right, my head is stuck in 2 dimensions, right? So in general, it's an algebraic integers. Degree is the dimension. Thank you. So here's a question, an exercise, if you like. Take this A. Okay? Give me the degree of h8 to the 12th. Not easy. Okay. But let me just state, let me give you the answer, sort of. So what I'm going to do is define 2 sort of random looking sets of vectors. So let's let, what am I going to call them? P be the rays in the fan for projective space. So this is negative E1 dot 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 negative ED, and then the sum of all these things. Okay, that's one set of vectors. These are the standard basis vectors. E1 is 1, 0, 0, 0, 0. What's that? No, I do not. Thank you. Thanks. And then the next set is, the next set I call U. And it looks a little similar. Whatever. 2 sets of vectors. Should be the same number of vectors in each set. Yes. Okay. So here is the proposition. The degree of a monomial map HA is the following. You take the sum over V and P of the max over U in U of AVU. You're going to keep seeing things like this coming up in this talk. Okay, so in some ways it looks like, very similar to what I had before. The difference is now I have a sum of linear recurrences. That's fine, still linear recurrence, but a maximum of linear recurrences is not necessarily a linear recurrence sequence here. This max causes things to behave very unpredictably, okay? If you keep changing which vector U maximizes, if as you take powers of A, the vector U that maximizes this keeps changing, then it's very hard to understand this quantity, right? So where do I want to go from here? Okay, I don't think these theorems are too hard to remember. If I need to refer back to them, they'll be the BDJ and the BDJK theorems, or the D equals 2 and the D equals bigger than 2 theorems. So a remark here is that if all the eigenvalues of A, I am going to give an argument for this formula because it's relevant for what follows. But before I do that, if all the eigenvalues of A are real, then for large n, the vector in U that maximizes a to the n VU tends to stabilize. I guess I should say, especially if you've got like one largest real eigenvalue here. Okay, this is not quite right even in that case, but close enough. It tends to stabilize, okay? So what looks like a max you can forget the max after a while. You're always just plugging in the same u when you evaluate this inner product here for large n. And then you really are looking at linear recurrence stuff again. Okay, so on the other hand, if you've got leading eigenvalues and they're complex conjugates, then you get sort of these rotations built in, and you never get this kind of stabilization. And then the max is relevant for all n, all right? So the upshot is there are two theorems that come out of this. One is, so not long after we wrote our paper together, Fav noticed this one. You have a monomial map in two variables. Then some power, some iterate of HA is stabilizable. If and only if some power of A has real eigenvalues. Okay? So, well, I didn't want to. So, to first order, it tends for large n. You always have for large n and a given v. You always have the same u. Actually, might go back and forth between two different ones, but think of it as just this given v. This vector u that occurs in the max is always the same for large n. That's a close enough approximation to the truth. Okay. All right, I also don't need my outline. Okay, a few years after Fav, Hasselblad and Propp Hasselblad has two T's, two S's? Right. What's that? Two S's, thank you. They observed that there exists 3 by 3, or there exists an A in SL3Z such that the degree of HA to the n, this sequence does not satisfy a linear recurrence, which is what I was suggesting anyhow when the leading eigenvalues of A are complex, but they, made it explicit with a very particular matrix here. All right, so what remains for me concerning monomial maps is to explain where this formula comes from, and for that I need to talk a little bit about toric d-folds. So, I'm not going to give a course on toric manifolds here. I'm not qualified anyhow. So I'm just going to, say enough to hope you get a general idea. Okay, so I'm going to let this kind of blackboard bold T denote C star to the D, the D-dimensional complex torus. Okay, not hard to check that HA restricted to the torus is really nice. It's an endomorphism. It's a covering map, unbranched. Okay. So I'll use that as an excuse to consider what HA does on certain compactifications of the torus. X. Okay, and I'm going to give you a very non-standard definition of toric d-fold. So there's a kind of canonical holomorphic volume form on the torus, and if you take any compactification of the torus, you can extend this to a meromorphic form on the compactification. So a compactification, a smooth compactification of the torus is toric if this is the form induced by eta on X only has simple poles and no zeros. On X. This is not the Fulton definition of toric d-fold in many ways. Okay? I'm trained to give 50-minute lectures because I'm sort of at sea as soon as you give me a different length of time. All right, right. So P2, for instance, is a toric surface, and it's got three simple poles for this form, the coordinate axes and the line at infinity. So the picture is this, and then you can ask yourself, how do you get more toric surfaces? Maybe by just blowing up points in P2. So you could blow up a point which has nothing to do with the coordinate axes, but if you do that, you're going to lift eta to a form with a zero at that point. Okay? You could, oh shoot, my definition's not working, is it? Okay, so I'm going to change my definition in a second here. You could blow up a point, a smooth point on the poles, okay? And then if you lift eta to a form here, you get nothing for this eta. You get no poles at all. So this, my definition is wrong here. And what's that? What's that? Yeah, right. X, yeah, that's exactly right. So that's what I should have said. So X minus, yeah. if x minus t consists of simple poles. Right, thank you. That's what I want. Okay, so now I've introduced some stuff that is not in the torus, but not in the poles either. So that leaves one possibility. You've got to blow up one of these 3 points. And if you blow up one of these 3 points, it's good. Okay? So, you know, if you blow up this point, then here's a new toric surface, P2 blown up at the origin. And then you can blow up any of the intersection points from the poles and keep going like this. So very concretely, if you want to produce toric surfaces, start with this triangle and just blow up successively blow up intersections between old poles and new ones here, okay? And something similar holds in higher dimensions too. It's just that in higher dimensions, what takes the place of the triangle is difficult for me to draw because it's 3-dimensional. You have a sort of a pyramid here, and you can blow up these points is fine, but you can also blow up edges. You have more possibilities for blowing things up to get new poles, all right? So very concretely, if you're only worried about things you get from blowing up projective space, there's a recipe for doing this that's completely explicit. All right, now, I need to recall a little more. A toric d-fold is somehow determined, let's call the d-fold x, is determined by its fan sigma of x, where sigma of x is a partition of RD into open or relatively open convex cones of dimensions 0 through D. And what else do I want here? Such that if you've got a cone in sigma, every face of that cone is also in the fan. And secondly, the top dimensional cones, since I want smooth here, these things, are generated by bases for ZD. Generated as a cone. By a basis for ZD. Okay, so this, I think that's more or less enough here. So for instance, let's take P2. I have my triangle, and where's my eraser? So you can get a fan for P2 if you take all the cones in this picture. So this is R2, this is P2, and these lines, this is the origin, this is the vector 1, 0, 0, 1, and -1, -1. Okay, so that is the fan for P2, the origin, these 3 open rays, these 3 open two-dimensional cones here. Okay? So in general, sigma of PD is equal to the cones generated by subsets of, where are those sets? Subsets of P. That P over there, okay? And if I were to, well, okay. So what I want to say, this is, I'm going to leave the correspondence between fans and toric d-folds mostly mysterious. The one thing I want to emphasize, though, is that the rays, the one-dimensional cones, correspond to the poles of the form in X. So the rays tau in sigma 1 of X, somewhat canonically, index poles h tau of eta in X. So X minus the torus is a union of things like this, things that are indexed by rays in the cone. So P2 has 3 poles. No coincidence that the fan has 3 rays. This one corresponds to the line at infinity. I believe this one corresponds to the vertical axis and this one to the horizontal axis, but don't quote me on that. Okay. All right, and if I were to, say, blow up the origin and work with, let's change boards. If I were to blow up the origin in P2 and work with this as my X, then there's a very nice way to get the fan. So I blew up the intersection between H that and H this, and what I do is I take the shortest integer vectors in each of these rays, add them together, get a shortest integer vector generating its rays, okay? And this ray indexes the new divisor here. So in general, if you take any 2 toric d-folds, X and Y, and you take the identity map on the torus, this extends to a rational map. What I want to call it, I'll call it pi. It's not really a morphism in general. From X to, it extends to a birational map, such that pi takes the pole indexed by tau in X and takes it to the pole indexed by tau in Y, provided that ray's in the fans for both X and Y. Otherwise, you get some contraction or indeterminate behavior for pi. So this gives you a nice way. So, this gives you a nice way to just sort of compare things between various toric d-folds. And in particular, it gives you a nice way to compare divisors. So also, if you got a divisor on x, and I've taken to calling this external, i.e. d is equal to the sum over the rays in the fan of x of, some integer or some multiple of h tau, then we can associate to that a support function, which I will call psi d. I'm going to, notational note. I'm going to use a little psi now. Later there will be a capital psi, which is only loosely related to little psi. The notation is not going to stay ideal. I probably already used the same letter to mean different things. It's going to keep happening, so just ask if it gets confusing. Okay, so you have a support function, psi d, on Rd, obtained, so into R, obtained by, let's see, I want to keep that. By setting psi d of v equal to c tau, if v is the shortest integer vector on some ray tau in sigma 1 of x. So I've defined it at finitely many points, and extending linearly to all the other cones, or all cones of sigma x, regardless of dimension. So this completely specifies the support function. And on the face of it, you think I'm just sort of like taking something very simple and making it pointlessly complicated. But the virtue of this point of view the virtue of this from my point of view is this. If that transition map is actually a birational morphism between two toric d-folds, this thing that is the identity on the torus, and you take a divisor that is external on x, then this psi d, it's the support function for d, but it's also the support function I went the wrong way. Okay, I should have taken the divisor here, because I'm going to pull it back to here. Okay, it's also the support function for the pullback to x of d. All right, so this thing has a kind of invariant meaning. It tells you what to do with any new poles that you create when you blow up. Yeah, in any dimension. No. No, I need a morphism. Yeah. Yeah. So what would work here? Yeah, I'm thinking of just take the line at infinity and the transition from P1 cross P1 to P2 or something like that. I'm not sure that's an example, but it gets confusing. Yeah. Right, what is... Oh, right. So I want to mention, I only want one particular support function. So e.g., if you take the hyperplane at infinity in PD, then the support function for this thing is support function at V is the maximum over U and U of the inner product of V and U, where U is this set. So now you sort of see the reason for both of these sets. It's still not the, I haven't completely tied this to the degree formula for a binomial map, but at least both of these sets of vectors have shown up here. So think of this as an exercise you can try. Okay, so finally, I'm almost there. If you have a curve on X, so by curve, I mean irreducible algebraic, it's internal, meaning it's not contained in a pole, intersects the torus somewhere, then actually PD is enough. Then there exists a toric blowup pi of PD adapted to C in the sense that each point of C outside the torus, so I'm really talking about the strict transform of C in X. Maybe I'll subscript this to lies in a unique pole of X. So you don't have intersections between C and two different poles at the same time here, okay? So I then associate a measure to C. So I'm going to set mu C equal to the sum of delta V over tau in sigma 1x times the C dot H tau for each ray in the fan of X. I'm going to take the intersection number between C and that pole, and I'm going to associate a point mass. And V is, as usual, the shortest integer vector on T. The primitive vector. Short as possible. Okay, so you do this. It's just it's again, maybe over elaborate. It's just a finite set of finite sum of point masses here. But again, it has a kind of invariant meaning because it doesn't matter which adaptation of C you pick here. You're going to get the same measure as long as you have something well adapted to C. And the upshot this time is, as a curve in P2, C has a degree, and that degree can be computed by just taking the support function. So the degree of C is line at infinity intersected with C. Let's count the number of intersections with this particular hyperplane. And this is just the integral of psi d against mu C. Okay. Say again, Chase? H infinity, thank you. Yeah, this would work for other divisors, but this is the case I need here. All right, so now I can give you my explanation for this degree formula. Maybe I can do it right here. So one more proposition. If you have an internal curve and you have a monomial map, then certainly the forward image of that curve is internal. With mu of HA of C equal to A star mu C, full stop. All right, you just take the matrix A and apply it to all these vectors. What's really going on here, proof HA of H tau is equal to H A tau. This is true as sets. If you include multiplicities here, I mean, this also accounts for multiplicities because A won't necessarily take a primitive vector to a primitive vector. So if the image of the primitive vector on T goes forward to something imprimitive, that just means that you have some branching here. So when you push forward this measure, you might get some support on non-primitive vectors here. But this modulo that qualification, I mean, this is what you get out of this. So it's very convenient here. And now my degree formula, hence, the degree of HA to the n is the integral of this thing against d mu of HA to the n of C, which is the integral of psi h infinity a to the n star. Actually, I should take L, where L is a line. Okay, so my formula for the degree of HA to the n comes straight from this thing. And you get an integral. And when you unwind the integral, that's all you end up with. Right there, you get the degree formula for the monomial map. Okay, so that's my take on degrees of monomial maps. And I'm going to recycle it. Fairly short order. All right, now, monomial maps are part of the maps in the theorems, the BDJ and the BDJK theorems here, but they're only part. There are some other maps which are not monomial, but still good on toric varieties. So let's go to this board. So here's a fact, which is very surprising to me. In every dimension D, bigger than or equal to 2, there exists birational maps G from PD to PD. There exists non-monomial which are nevertheless toric in the sense that G star eta is delta eta. Okay, it still pulls back this holomorphic form on the torus and just gives it back to you with a multiple. But it's not a monomial map. Okay, so this is a little surprising. You can take G of this form. You start with a monomial map associated minus the identity matrix. So this is the standard Cremona involution, and you twist it up, where B is an automorphism of PD. Okay, not just any B, but you can take, there exists B, so that this is an example of something like this. So when D is 2, I think I'm going to have to look. Yeah. This will do. Okay. And when D is 3, I'll stop after this one. Again, I have to look. Right. Those matrices work. I have an explanation of why this works that makes me happy. I'm not going to give it. I have no explanation. Actually, I have to, okay, so it's maybe not good form to attribute different pieces of a joint work to individual authors, but Mattias thought that up. And I asked him again a couple weeks ago, where'd you get that? And he's like, I don't know, I just played around. So he got one in every dimension, and that's good enough. Okay, so if you take G of that form, where's my eraser? So from now on, when I say G, I mean this G, and I mean I have the right matrix. You get the following facts about G. G right. You take any pole, so you pick a toric d-fold in which that pole lives, lift G to that toric d-fold, and G just sends that pole to itself. Okay, that is crucial. Also, G inherits a lot from its parent here, the standard Cremona involution, so G has d plus 1 exceptional hyperplanes, even in P2, or in any surface. And they're all internal. They all meet the torus, so G is not a monomial map. And for each H, G of H is a line in some pole, okay? You can explicitly work out which poles contain these lines. When d equals 2, the image poles are the ones are indexed by the rays in the fan of P2. So they're the ones that come from, is that set up there on the board yet, U and V? I think I got rid of it. Or U and P. There was a set of vectors P, and they're the poles that come from the vectors in that set. Okay, if d equals 3, it's generated by 4 vector. When d equals 3, the image poles have rays generated by vectors in some set V. I'm not going to write V down. It's just not P anymore. So the image poles are no longer the poles in P3 here. Okay. I want to say more than this. So because of these things, you get a formula. So if you have an internal curve with its associated measure, you get a formula for the measure associated G of that curve, which is kind of like this one. Okay, so corollary of these observations, if C in PD is an internal curve such that it does not contain any points that are indeterminate for G, and for every exceptional hyperplane of G, H intersects C is in the torus. Okay, these are fairly generic conditions on C. Then the measure associated to G of C is, for starters, the same as the measure of associated to C, because of this fact, and that H is birational, so there's no branching about poles. But you also pick up some stuff from the intersections between C and the exceptional hypersurfaces. So for that, let's see. So you get these conditions are to guarantee that I can just put a degree C here. The number of intersections of C with H is just a degree of C, and they're in good position. Okay, times the sum over the delta masses at points in this set V. All right, so I'm just going to call this delta script V here. Okay, so finally, after all that, I can tell you what the maps are in the main theorem. All right? Yeah, sure. It's extremely convenient to have the poles fixed. And it turns out that it's not obvious staring at this that happens, but if you actually write down the formula for this G, the first component is x1 times something, the second component is x2 times something, and it's our x0 times something and x1 times something. And so you really do fix x0 equals 0, x1 equals 0. But you have to, the shortest way to do it is through formulas. Yeah. Oh, one thing I forgot to mention, I never said anything about the indeterminacy set of G. Again, because this is coming from the Cremona involution, the indeterminacy set of G is the union of the intersections between the exceptional hyperplanes of G. So you intersect any two hyperplanes, that's indeterminate. Okay, so what I really want to avoid with my curve is these intersections here to make this formula work. Okay? All right, so finally, the maps F in theorems BDJ and BDJK have the form F equals HA composed G. I think in one of the papers we might have switched these two, but this will do. For appropriate D by D matrices A. All right, and in last 10 minutes, let me tell you what you want from A here. It's easiest to explain what HA is in dimension 2. So in dimension 2, you're going to take, that's supposed to be a zeta, a Gaussian integer zeta, such that the argument of zeta is irrational. So you could take 2 plus I. If you wanted. Yeah. What's that? Not. Thank you. And then you let A be the matrix for multiplication by this thing. Okay. So when D equals 3, you start actually in higher dimensions, periods, and d is greater than or equal to 3. You want birational, so you're going to start with an invertible integer matrix, A tilde, and you're going to take, you want some conditions on A tilde, kind of like this zeta, with a couple things. Irreducible characteristic polynomial. And eigenvalues C1, C2, C3, where C1 and C2 are just conjugates of each other, and zeta is as before. So this guy has to be some real number. And again, the argument of zeta is not in Q. And the third eigenvalue is smaller than the other two. Okay, so you want the leading eigenvalues to be these conjugates. And I'd like to say that's your A, but I put a tilde on it, so it's not my A. All right, so what did I do with my eraser here? So what you really want is to take a high power of A. And if I'm being completely honest, I should add the word suitable conjugate of. Okay, which this last thing is very annoying and leads, it accounts for about a third of that paper with the BDJK paper, all right? But we can ignore it for the moment, okay? So in either case, you can use, the composition of F to get a formula for the measure associated to the forward image of a line. Okay, subject to conditions on the line. So I know how to get mu of G of C, and I know how to get mu of HA of a curve. So I just iterate those facts, and you get mu of F to the n of L is A to the n star mu L, which is what you would have got if you had a monomial map. Okay, if you just had HA. Okay, so there's a piece that just comes from the monomial, but then there's another piece which is sum j equals 1 to infinity of, let's see if I can do this, right, the degree of f to the j times what I'll call psi of a to the j or no, it's not time for that, sorry. Times a to the n minus j plus 1 star of mu v, this measure associated to the set of vectors v. So you just get this recursive formula for the images of a line. But you got to be careful with the line. So when you map the line forward, you want to keep using, where is the formula? Right here. You want to keep using this formula applied to sort of forward images of L. All right, but this formula has conditions on it, so you need to make sure that the forward images of L satisfy those conditions. So this is going to work if f to the j of L is good for every j less than n, I believe. Okay. And this fact here, where am I at time-wise? Yeah. Is a little bit tricky to arrange. It explains, it's always going to hold in dimension 2 if I take my matrix A to be of this form, okay? But in higher dimensions, it doesn't work for the original matrix A tilde, or at least it's not clear whether it works. What is clear that if you take a high power of A tilde, it will start working, all right? So that explains the fact that I want to take a power of the original A tilde at this point, okay? So I'm not a big believer in going over time. I wanted to get a little further than this today. So I think I'll just stop here and pick up with this next time. I'll finish the geometry and start talking about the number theory. So we'll stop there for now. Many. In the end, I mean, so as I said, in dimension 2, I mean, this is all you need from your matrix. So there are lots of Gaussian integers with irrational arguments, and you can use any of them. The one thing is, maybe I should say this, is if you take A to be invertible, you will never have an irrational argument. So this is the moment at which it becomes impossible to take the two-dimensional example to be invertible here. In higher dimensions, it's not hard to produce lots of matrices like A tilde here and getting the appropriate power. I haven't said anything about what's appropriate for this, conjugating matrix, but that's pretty generic too. There's a fairly, the idea is you should just be able to take some random matrix and conjugate your original thing with that, and that should be good enough. So there are lots of examples there.
I have a question.
Yeah.
So the way you wrote the map with HA on the left,
Mm-hmm.
if you compose them with the translation on the torus, does the dynamical degree, does it stay also transcendental?
Right. Yes, in these examples, let me think about it. If you took either the maps the way I've set them up there and you compose with the translation on the torus, that would not affect anything about the degrees. Since you mention it, though, there is something I've wondered but never really checked. And I said I'm working over C, not some field with relatively few elements in it. I mean, it's an uncountable field. So I do have the option of composing with a translation. And what I'm wondering is if you could use that in place of this power right here. The power is just to guarantee that when the forward images of my line are good for this corollary right here. But maybe if you just sort of shift everything by a random translation, you know, for other reasons, the images of your line will be good. So
really you get families of transformations with transcendental dynamics.
yes, you get right families, and I don't have the argument that those are not. I mean, you could ask, well, but maybe they're all conjugate to each other or something, right, in some tricky way, but I don't think so. I haven't checked that. Yeah.
Okay, all right.
Okay, thank you. Right. I don't know. So something has been done with lambda 2, and I will mention that maybe next time. But I would love to have something like this for higher dynamic or higher degrees of the maps. It's tricky because then you're not mapping lines forward. You're mapping, if you want the second degrees, you're going to have to map planes forward and keep track of how they intersect poles. But I don't know how hard that would be. I just have not tried at this point. I think it would be really nice to have formulas like that. Yeah.
All right. Well, let's thank Jeff again.